Okay, let's get started. So, in this case here, we will be looking at a question that is basically checking up on how you understand the principle of conservation of mechanical energy. Now, there are a number of formulas in this case, but I want to highlight two of them, the differences between the two. But seemingly, they still work with the same principle on the principle of conservation of mechanical energy. Now, the first one here, the first question, it says calculate the speed of the trolley at point B. But let's first read what information they have given us, and then we'll go to the figure below. So in the figure, a dynamic trolley of mass 1 kilogram moving at 3.5 meters per second rolls from A to B along a frictionless runway. And then they also tell us that the length of the runway is 1.5 meters and the vertical height between points A and B is 0.5 meters. So let's look at the diagram. As you can see, there we have our trolley. It is 1 kilogram. And then the initial speed of it from point A to point B is 3.5 meters per second. The length, the horizontal length on the runway going up is 1.5 meters. But then we're also told the vertical height of it being 0.5 meters. Okay. Now, the first question asks us and says, calculate the speed of the trolley at the point B. Right, at the point B. Now, in this case, what do we know from what we are told? Firstly, is that at the beginning we have a 1 kilogram trolley that is moving at 3.5 meters per second at point A, but it has to move from point A to point B at the top, but it's on a frictionless runway. If that's the case, that tells us that we can use what we know as the mechanical energy, right? We can use the conservation of mechanical energy formula. Now, in your lower grades, maybe in grade 10 or 11, you may have seen a formula where you'd say the sum of the mechanical energy before plus is equals to, to the sum of mechanical energy after. Okay, so let's use that. Let's use that because it is in a frictionless runway. And just to remind you again, what is the principle of conservation of mechanical energy? So the principle of conservation of mechanical energy states that the total mechanical energy or sum of gravitational potential energy and kinetic energy in an isolated system remains constant. A system is isolated when the resultant net external force acting on the system is zero. Okay, so let's ignore maybe the last part of it where it says the work of non-conservative forces, and non-conservative forces is what? It is supposed to be friction, supposed to be all those other things which would be external to the system, right? So in this case here, we have a frictionless runway, so we can use mechanical energy, the principle of conservation of mechanical energy. Now there's actually two ways of actually calculating this, right? But I'm going to show you the first way, which would be maybe your go-to method if you remember some of the work that you had done in previous grades. And that is the sum of the mechanical energy before, which is at point A, right? This would be at point A to point B, and the sum of mechanical energy after, because mechanical energy is basically the kinetic energy plus the potential energy, right? Or kinetic energy plus the potential energy. So in this case, as you can see, we have the kinetic energy initially, right, at the beginning, at point A, basically at point A. And then we have the potential energy at point A as well. But in this case, with potential energy, what actually changes here? It's the H, right? Because at A, it's at a particular height, and then at B, it's at a different height, right? So we put a B and B there, right? So you have your mechanical energy sum on the one side, right? Which is talking about at point A. At point A. Where's point A again? Here's point A, right? There's point A. And then to point B. Now, what do we do? Automatically, you should remember that with the trolley at point A, what did they tell us? They first told us, obviously, the mass. So we know that the mass is 1 and 1, right? But then the speed, we actually are told the initial speed at point A being 3.5 meters per second, right? To climb the runway, right? However, you would notice here that we have mgh, right? And the height at A is actually 0. But g is just the gravitational acceleration and its mass. Gravitational acceleration doesn't change, so it's just 1 times 9.8 times 0. And so it's just 0. Okay. But now remember, what are we actually looking for? We are looking for the final speed. The speed at which this particular trolley will be at B. Therefore, when we put in our information here as well, you put in your mass as 1, and then your mass is 1, and you put in the rest of the information, 0.5 here, and then you actually find that you have half the velocity final at B squared plus 1 times 9.8 times 0.5. And then obviously when you solve it through, you're supposed to find that the final answer would be 1.57 meters per second. And this is the final velocity at where? At B. Right. At B, that's how much we expect the speed to be. But if you just think about it before we actually go on, if the final velocity at point B is 1.5 meters per second, I think we can both expect that this particular trolley can still go a bit further than the distance that they had given us being 1.5 meters, correct? So we can expect that it would move a bit further than the 1.5 meters. Okay. Now, here's the second question. Now, the second question is where things get a bit complicated. But before we go there, let's first do a second method to just verify that this formula that they had given us here does work as well. So in this case now, when we actually try and verify it by using this formula, notice that when we expand this formula where we have the non-conservative force is equals to the change in kinetic energy plus the change in potential energy, right? As you can see, with the change in kinetic energy, we would have the final velocity that we're looking for over there and the initial velocity there. So this is the final velocity at B and the initial velocity at A, and then we have the height at B and then the height at A, and it's subtracting, right? And so when we talk about the work done by the non-conservative force, then we'd say F of the displacement x cos theta. Now, how can we use this formula? Because remember, in the first one, we used this one here, which was actually quite more simple because you didn't even have to use the work done, right? You didn't need to use the work done formula of non-conservative forces. In this case, in actuality, if you understand the principle, what does the principle of conservation of mechanical energy state? says the total mechanical energy, which is the sum of the gravitational potential energy and kinetic energy in an isolated system, remains constant. But this part here where it says in an isolated system it remains constant, this is what it means. It is a system that is isolated when the resultant, right, resultant net external force acting on the system is zero. Right. Now, the resultant net external force is zero. If the external net force is zero, what does that mean for us? Because we are calculating a system which conserves mechanical energy. That means when we look at this formula, it would mean the force here is actually zero. Right. So in truth, you'd have 0 times the distance that you are given. It's 1.5 meters, right, of the plane, and then cos 0 degrees, right? And then you'd have everything else that you needed, which would be a v squared. If that, this is the final velocity, minus 1 over 2, it's 1, here it is 3 point, I think 25, 3, no, 3.5, 3.5 squared minus mg, which would be the, oh sorry, that's supposed to be an addition right there, so added, so that's add, and then we'd have mg, which is 1, and then that would be 9.8, right? And then we have the height, which in this case at v it's at 0.5, it's at its basically highest height, right? And then you finish off there with 9.8, right? And 0. And then as you can see here, if you think about it, as you solve all this, it will result to the same final velocity that says the velocity is 1.57. I am sure, I think it's 1.57. Let's check. Yeah, 1.57. So there it is, 1.57. Okay, so we've done it in two ways. How to calculate the speed of the trolley at point B. Right, but now, as you saw, the one here, we use the non-conservative, the work done by non-conservative forces is equal to the change in kinetic energy plus the change in potential energy, right? And it worked quite well. But also, when we used the one that we know from previous grades, it also works quite well as well. When we use the mechanical energy, the sum of mechanical energy before is equal to the sum of mechanical energy after. It also works. So, there's obviously a connection between these two things. You'd actually find that if you had to take this formula over here, right? This formula over here, and play around with it a bit. And why I'm explaining this is because it will help us in understanding this question over here. So, if we had to play around with this a bit, let's move things along. Let's just move things from one side to the other. Let's put the A's with the A's and the B's with the B's, meaning the velocity at point B with the height at point B, and so on, right? So that would have meant we would have had the kinetic energy, right, at B, plus the kinetic energy, potential energy, sorry, at B, minus, minus what? The kinetic energy at A, and let's put a bracket there, plus the kinetic energy, the potential energy, sorry, at A. Right. So now we have that. Since we have that, don't you notice something? What is mechanical energy? Remember, mechanical energy is the sum of kinetic energy with its potential energy. Right. So you actually have here the mechanical energy at B, right, plus the mechanical energy at A, which is actually all equals to the work done by non-conservative forces. But this is telling us something quite interesting. Not plus, it's a minus. But this is telling us something interesting, because if we take maybe point A and put it on the other side, then it would have been the work of the non-conservative forces plus the mechanical energy at A is equals to the mechanical energy at B. But what is this telling us actually? What is this particular manipulation of the formula telling us? It is telling us that from our previous grades, we always used to use the sum of the mechanical energy at A, or at a particular point, to the sum of the mechanical energy at B, right? And that would have been in a case where there isn't any external forces acting on it. That would have been the assumption. We just knew that there's no external forces acting upon it. But now, since you're in grade 12, there are cases where now there's external forces acting on it. But how can we work with external forces when we're talking about mechanical energy? This is where the work done by non-conservative forces comes into play. And that's why we have the work done plus that mechanical energy, which is, remember, mechanical energy is being that it's the kinetic energy at that point plus the potential energy at that point is equal to the kinetic energy at the other point plus its potential energy at that point. You see, so that's why we have this particular formula. That's why it was so important for you to be able to understand the importance of the work done by non-conservative forces is equals to the change in kinetic energy plus the change in potential energy. Right? Because it gives us the ability to work with the external force of the system, because now it's not isolated. So now there we go. Here's the second question. It says, now suppose the surface A B, right? The surface A to B is rough and the trolley experiences a constant frictional force of 5 newtons. There we go. So once they tell us that it is experiencing a constant frictional force of 5 newtons, that tells us what? Now there is an external force. Now there's an external force. And which one of the two equations will be best when we're working with an external force? It will be the work done by non-conservative forces is equals to the change in kinetic energy plus the change in potential energy. So as it moves from A to B, will the trolley reach B? Justify your answer by means of calculation. But luckily, we understand now the principle of conservation of mechanical energy and when to use which formula and how to use it. Now, firstly, we know that when there was a frictionless surface, we could just use the mechanical energy sums on from one point to the other, right? We could just use this basic one, yeah. But now we have frictional force. So now we need to use the work done by non-conservative forces is equals to the change in potential energy plus the change in kinetic energy, right? Or potential in kinetic energy, right? And so, now, the question itself, we know what to use. We know which formula to use. But now, what are we actually looking for in this formula, right? What are we actually looking for? Because they just said, will the trolley reach point B? Will it reach point B? How can we tell if it will reach point B or not? What is something in this formula that could help us to tell whether or not it would reach point B? It is what? It is the distance. It is the distance, right? It is the distance. Not the height, but the distance, the length of the runway, right? It's the length of the runway. Previously, when we calculated the speed, we put in that 1.5 meters. But in this case, we actually want to solve the distance of this particular um, um, movement of the trolley. But why is it the distance? Think about it. If this now, because it has now an external force or friction, it has a frictional force of 5 newtons. That's obviously going to be working against the motion of the trolley. If it reaches B, we expect what? We either expect that the distance of that formula would be 1.5 meters or more, right? If it reaches, so let me write this, if it reaches, right, then the displacement or the change in x would be either greater or equals to 1.5 meters. But if it is not, then the change in x will be less than 1.5 meters. Okay, so you see these two things. If it is more or equal to 1.5 meters, it would have reached point B. But if it is less, then it wouldn't have reached that distance. And how can we be sure about this? Think about it. It needs energy to go up to point B. At the beginning, it was on a frictionless surface. It reached point B, so therefore we were sure that we can put in 1.5 meters as the distance from the very starting point to the ending point. But now we don't know if it would or would not reach point B. So how can we fix that? We know now that the only force that they have included in this case is the constant frictional force of 5 newtons. So now the constant frictional, the frictional force would go in the place of F, right? And would be our F net of the external forces in the system. But as this is going, remember the frictional force is moving against the motion of the trolley. Therefore, you know what your cos will be, right? But now, your x, which would be the distance or the length, right, of the runway, you have to think of it as saying that if I have frictional force, how far will I go knowing that I have a change in mechanical energy, a change in kinetic energy plus the change in potential energy? Do I have enough energy to get to 1.5? So this is the solution to that, right? This is the solution to that. As you can see, we used the formula of non-conservative forces is equal to the change in kinetic energy plus the change in potential energy. And then we actually calculated. And when we calculate it like this, you actually find that it's 1.5, blah, blah, blah. And then we put in all the numbers that we know, right? And then we get to this point where we have to do this part here, right? But obviously, the frictional force is basically our F net of the external forces, right? So we put 5. And then it's cos 180 because it's going against the motion of the trolley. But we already know that here the change in kinetic energy plus the change in potential energy is supposed to be negative 1.225, right? And so if it's negative 1.225, and we actually find because of cos theta, cos 180 degrees, then that would be negative 5. So we divide that and we actually find that the distance would be 0.245 meters. So that is as far as this trolley will get with a frictional force acting upon it. And because this is less than 1.5, therefore we have that no, the trolley will not reach B, right? B. And that's basically it. And so I hope you have taken out of this video two things: the difference between what you had learned previously in the previous grades about mechanical energy, and now how we have modified it in grade 12 to work with external forces, right? Or external things, right? Because remember, this is what it says. It says, principle of conservation of mechanical energy states that the total mechanical energy in an isolated system remains constant, right? But it says a system is isolated when the resultant net force acting on the system is zero, right? So when it is zero, then we actually have what we know as our old formula, right? As our old formula. And when it is not zero, when the external forces are not zero, then we use the work of non-conservative forces to find the solution. So I really thank you for watching this video. I hope that it has been a good experience and you've understood what is being said. Other than that, I'll see you next time.